days now. But I've been using SQL, the language, for a little over 26 years. So watching it grow and change over time has been fun. But it was amazing to me, some 25 years ago, to be able to take hundreds of lines of procedural code and turn it into a simple select with a join condition. Instead of having to open two files, position a pointer into the file, use VCM to read key reads and put records together. You just go select star and print depth where a join condition. And so SQL was pretty powerful back in the early days. Some queries, correlated subqueries, DMP join, where clause, and everything. But it was still a little lacking in doing certain things. So what I'm going to do today is talk about 5, not necessarily new things that have come into SQL, but 5 things that over about the last decade, the last 13 years, have come into the SQL language to allow us to do much more powerful things. Instead of just being able to join and look left and right in a row, we can do things like look up and down in the result set, procedurally process a result set, have a table be a function instead of just a database table, use data sources, different images, database tables, use things stored outside the database, and then more recently be able to apply procedural code inside of our SQL statement, not writing in PL SQL, but writing in a spreadsheet-like language. And today in version 12, moving on to row pattern matching, being able to apply regular expressions to streams of information. So before I begin, I have to do a small print. I'm not planning on talking about futures at all. Everything I'm going to be talking about has either existed since Oracle version 8.6 through version 12c. And so I'm really not anticipating mentioning anything coming in the future. In case I do, this is my introduction to free. So all of the examples you can see have actually been run in production versions of the database, so nothing that's coming in the next release. The first one that I want to talk about is analytic functions. Analytics have been around in the database since version 8.16. I knew about them myself in some detail when I wrote my first book back in the turn of the century, Expert on Oracle. I wrote a chapter on analytics that forced me to really look at analytics and learn them inside and out. And frankly, I think I've used analytic windowing functions to answer more questions on ASCOM than any other construct short of the select keyword. So we're going to take a look at some examples. Before we do that, let's look at what an analytic function can do, or how to explain an analytic function to someone who's not used them yet. Basically, these analytic windowing functions give us ordered array-like syntax, if you will, on a result set. In SQL, in the beginning, you have a select statement. There's no such thing as a first row or a last row, or a row in front of me or a row after me. I'm going to use an order by statement, and I have the appearance of a first row and last row, but SQL itself didn't understand this concept at all. So it just gave me a result set. With these analytic windowing functions, we start doing things like logically partition this data. Okay, I want to process by department. I want to do something by depth. For example, I want to find the top 3 paid people in each department. So I need to do some processing by some dimension in my result set. So we have this partition by clause. Optionally, we have an order by clause that we can throw in here with many of the analytic windowing functions. So I not only want to break this up by department, but within each department, I want to sort the data from big to small by salary. Once I've done this, I can start applying analytic windowing functions to it, such as row number, for example. So this very conveniently numbers each row in this partition after sorting by salary with an ascending number, 1, 2, 3. As I move from one department to the next department, this counter automatically resets. And I'm doing 1, 2, 3, 4, 5 now. Hopefully you can see how with this construct, getting the top 3 by something becomes an almost trivial operation. You could do this in version 8.5 and 4 with plain vanilla SQL. You could. It was difficult. The syntax was rather ugly. Typically involved lots of self-joins. And if you ran it on more than the 14 rows of the employee table, you were likely to be very disappointed by the performance. So while you could do it in regular SQL, it was hard to write and the performance was horrible. We'll take a look at a couple of examples of this now, just so you can see some of the things that you can do with this. So for example, computing running totals. During a report, you'd like to have a running total of the salary within each department. Percentages within a group for each employee showing how much this person makes as a percentage of the total salaries in that department. Things we typically might think of doing in our application. I have a firm belief that the more I can pack into a single statement, the better my application is going to perform. The database was really formed to work with this data. So let's take a look at some of these. Here's a running total. This is how easy it can be. I just need to say sum of salary over. Break the data up by department number. Okay, so we're going to logically partition this from 10, 20, 30, and so on. Then I break it order by salary from small to big. And that's it. That gives me a running total. I have two running totals here, though. One that's ordered by salary, and one that's ordered by salary, row ID. This is just pointing out a nuance of these analytic windowing functions. If you order by something non-deterministic, salary is not orderable deterministically because you might have more than one row with the same salary. The analytic functions no longer know which one comes first or which one comes second. So in many cases, when working with these analytic functions, you are going to want to make sure that you order by something deterministic. Because if you notice that salary, the running total column for Scott and Ford in Department 20, they both make the same amount of money, $3,000. So when I just order by salary, the database doesn't know which one comes first. So it says both come first. And so the running total looks a little off, because the running total is the same for both of them. But when I add something to make it unique, like row ID after the salary, or if I add an e-name in this case, or some other attribute that would make the sort order deterministic, I get a more reasonable looking answer. This is just something to keep in mind as you're using it. So what I've seen people do is write an analytic, get the running total one with that duplicate answer in there, and then say these things are stupid, they don't work right. Once you understand that you really need to be doing things in a deterministic fashion with your order box, this is going to apply for a lot of the other capabilities we're going to talk about, like the model class and row pattern matching. You need to have a deterministic sort order for these things to make sense. Here's another one, using a ratio of the report. See how easy it is to show any individual salary as a percentage of the total department salary. I just use this ratio of report function. I could do this in standard SQL. So for example, this is an approach many developers would take. If I wanted to get a percentage of a given row's salary with respect to its department, I would run two queries in effect. First, I get the salaries aggregated to the department level, then I join that back to the detailed information by getNo, and then file. It's pretty straightforward. The performance of this query, however, is many times worse than the performance of this query. This one needs to make one sweep at the data set. It gets the answer in one pass. This one needs to make at least two passes, probably puts a lot of data into temp, has to join these back together, get more data into temp, sorting, aggregating, everything else. The more I can do with fewer operations, the better off I'm going to be, especially if this emp table was millions or billions of rows. I only want to make one pass on this information. Analytics that will do this. Here's another one, the top end queries. And these are interesting to me for reasons other than just showing you you can do a top end query. Here I'm using row number, just like I did in the initial slide to explain how an analytic works. And so we're assigning number 1, 2, 3, 4, 5, 6, and so on to all of the rows within the emp table by getNo after sorting by the salary. And somebody's asked me to generate a report that shows the top 3 paid people by salary within each department. Here's my first cut at it. Looks pretty straightforward. If you ask me though, it's wrong. Because the question is wrong. And this is part of our job too. Somebody gives us a question to answer out of the database. We have to make sure that they understand what they're getting and we understand what they want. when somebody asks you for the top 3 paid people by department, do they really mean they want the first 3 people to come out after sorting? Or do they really mean, I'd like to see the set of people by department that make the top 3 salaries in that department? Business people never speak like that. They never use the word set or anything. They just say, who the top 3? If you look at Department 20, Scott Ford closed named 3,000. What if Scott, Ford, Smith, Blake, and Jones in Department 20 all made 3,000? Which of the 3 would you see? Every time you run a query, you could actually see a different 3. Even in the same database, with the same exact rows and bits and bytes on the disk. It would depend on the sort area size that you decide to use for that query, which one would come out. So what the business person probably meant was, I want you to rank these people. And so conveniently, there's a ranking function. So here I can say, put a rank on things. And notice in Department 20, 2 people tied for first place, and then there's a person in third place. There's no second place person, because the 2 people tied for first. Now here's where things get tricky. What if 4 people make 3,000 in Department 20? All of a sudden, you're not going to get 3 rows, you're going to get 4. So you're starting to get a set of people who need these things. I think the ranking function the business person really meant to tell us to use is a thing called bench rank, where even if there's a tie for second place now, I get somebody in second place, and now I'm getting 4 records. This is convenient because if 50 people make the highest salary, and 25 people make the second highest, and 15 make the third highest, I'm going to get that set of people. No longer going to get just 3 records. I'm going to get hundreds of records. Why is this important? What if this was a report of salespeople who were going to win products for doing those sales? And so instead of salary, this was sales. Wouldn't you hate to be the salesperson who did the same exact amount of sales as everybody else, but your name doesn't show up on the list because Oracle decided to sort you last? And you run a query yourself, and you say, oh, Oracle sorted me first. Then you run it again, oh, Oracle sorted me third, and so on. And so with these analytic functions, make sure you understand what they're returning. Even more importantly, make sure you understand the question that's actually being asked of the data. So here's another one using another one of my favorite functions, lag and lead. Looking backwards in the result set, and looking forwards in the result set. It gives us the concept of a prior record and an next record. And here's an example of really using this. I'm using all objects, but pretend that all objects was patient information, for example. And so the object type isn't an object type, it's a patient name. And I wanted to find the average number of days between visits for patients. Think about how hard that would be if you're just using straight SQL. You have to join patients with patients by patient ID, but where the second patient ID's visit date is the minimum one that's greater than the current rows. So we've got multi-table joins, self-joins, generating Cartesian products that need to run a scalar subquery to find the minimum date that's greater than that date for that particular patient. That's scan after scan after scan of the data. Here I make one pass. I can just say, take the last visit date, which is created, take the previous created date, subtract the 2 from each other. I now have the delta in number of days between my 2 visits, and I just need to apply average to it. Once you get into these analytic functions, you're going to find millions of applications for them. Unfortunately, for whatever reason, they documented them in the data warehousing guide. So a lot of people building transactional systems don't even think of using it. But in an OLTP system, you still are generating reports like this frequently, and you might be looking at an individual patient. You need to find the average number of days between visits for a patient trying to display on the screen. Now, a patient has maybe 100 records, that's an OLTP operation. How do I do that SQL efficiently? It's not going to be by doing self-joins and scalar subqueries. It's going to be by using analytics. And hopefully, it's not by just letting the data out to your application and saying you do it all in Java. Right? You can do this easily and efficiently inside of SQL. using analytics to tune. This is a rather old example, but for me, it's been a showcase example. This was a piece of code that a customer was running. They were inserting employee information into a data warehousing table. So they had them know an end date, it was a status record. Here's what job I had until this date. Here's the job I had until that date, and so on. And then what they did was they went back and they did what they called a dedupe loop, deduplicate this information. So they might have inserted 5 records per year. And so I got 5 different end dates. Then they would go back and using this subquery, they would find the oldest end date of any one of my records and get rid of that one. And if they deleted at least one record, they would do it over again. And so what they would do if I had 5 records is this loop would execute 5 times. The first 4 times it would delete my oldest record. The last time there wouldn't be any records to delete, so there would just be my newest record. So after I analyzed this query and tried to figure out what it did, I realized what they wanted to do is keep the most current record out of this time series information for every employee. But it took me forever to understand this. And the reason I was trying to understand this is because the customer said, Oracle was slow, we had the best consultants ever, they built this ETL process, but it takes forever to load the data, it takes forever to query the data. So we're going to replace you, IBM came in and said they're much faster than normal. And sure enough, they put together a prototype and we pre-cooked the load and pre-cooked the query. Well, once I understood what this logic was, I said, this is the worst way to load this warehouse. Because think about it, if I have 5 records, you loaded all 5, and then you delete 80% of them. In the data warehouse, what do you do? You're scanning. I want to load this packed, compressed, and everything else. And so I'm going to get rid of all this procedural code and replace it with this one insert as select. I took their select statement, and all I did to it was I added, give me the maximum end date for each employee record. So it would take all of my employee records, and it'd have all 5 of my dates, but it would find automatically the maximum date out of my 5 and assign that to every record. So in the outer query, down at the bottom, all I have to do is say where my end date equals the maximum end date. But I also have some other logic in there that count. If you look at their procedural code, if I had 2 status records on the same day, it would get rid of both of them. So say you have an employee who was hired, but there was a mistake made in his records, so on the same day they changed his job title. And then they just had the date, not the time. They get rid of both records. The customer argued with me and said, no, that's not what it does. It keeps the most current record. I said, no, it doesn't. Yes, it does. I had to put data in the table and actually run it in SQL Plus and say, look, table's empty. And it gets rid of both. And I had that logic incorporated in there with this count. Right? And just counted how many end dates there were by employee number by end date. And I would only keep it if the count was 1 and the end date equal the maximum date by employee. That was a bug in their application that they didn't even realize. But they looked at this insert statement and they started saying, this is so complex, I don't understand this, I don't get it. And I went back and said, I didn't understand this, I didn't So all you need to do actually is comment this stuff and sort of explain before the code runs what the code is doing. And in order to fix your bug, all I did was I commented on that count, and the count was 1. But now I have sort of another bug. I might have 2 records for an employee. What do you want to do? How do you want to handle it? Tell me what you want to do with it. Give me the specification, and I can make an analytic function that's going to do it for you. And I could use the direct path load here. So I was loading 20% of the data. It ran the query once, so it didn't have to do that dedupe loop over and over again. I could use compression. Queries benefited from this, and all of a sudden the Oracle was fast. Right? It really just depends on how much you know about your database and how much you know about the SQL language as far as making things fast or slow. This is going to be the fastest way to load a table. Single insert, doing all the work, no procedural code. I've heard a saying, and I live by the saying, more code, more bugs. Less code, less bugs. In our industry, we measure bugs by number of source lines of code. So by definition, if you write less procedural code, you have less bugs. In theory. Another one, pipeline functions. This is another underutilized one. This allows you to write a piece of procedural code, PL SQL. I know I just said don't write procedural code, but sometimes you have to write procedural code. And you can use that procedural code in SQL as a row source, as a table. So, for example, I'm going to create an external table and map to a flat file. I want to load my data warehouse. So I've got this big file or set of files sitting out in the file system. Now I need to process this code. So I'm going to set an object type that looks like my external table. So it has all the same columns as the external table. I'm going to create a collection of that, sort of like an array. Now I can create a bit of procedural code. So this one just takes a cursor as an input. It's going to bulk collect. So we're going to do some array processing here. Get 100 rows. It's going to loop over those rows. I have a comment in there saying whatever code. This is doing whatever transformation or whatever I need to perform on the data. Maybe it's doing validations, it's doing lookups, it's doing some sort of transformation. It's the procedural code I need to apply to every record that's coming in from this external table, this file I want to load before it goes into the database table. Now, using this, I can simply merge into an existing table and transform information coming in from a flat file, update it when the record already exists, insert it when it does not exist. How would you typically do this? Well, many developers looking at an ETL problem like this would write a program. It's going to open the file. It's going to read the row from the table. It's going to do the transformation. It's going to try to update the existing record. If it didn't update anything, it would insert it. Guaranteed that's going to be orders of magnitude slower than doing it in a single SQL statement. Here, the data just flows from the disk into the procedural process, and in a bulk fashion it's merged into the existing table. When you're dealing with hundreds or thousands or a small number of millions of records, doing that slow by slow process is going to work okay probably. Right? As soon as you start dealing with millions and billions of records, doing things one at a time is going to completely fall apart. Suppose you had 5 million records to load. And suppose each record took 1 millisecond to go through all the processing. That's reading it from disk, that's doing all your transformations on it, and then that's updating or inserting it from the table. 1 millisecond is extremely optimistic. It's not going to be 1 millisecond. But suppose you could write it that fast. To load 5 million records, it's going to take you almost an hour and a half. To load 50 million records, we're at over half a day. To load 100 million records, we're talking about days of processing. Load a billion records, we're talking weeks. Oh, we'll just make it parallel, right? We'll split it up and we'll run 1,000 processes on our 4-core machine. We'll do this. That's not going to work either. You turn your data warehouse into an OLTP system by doing that. And instead of just waiting on disk I/O or CPU or something like that, you start putting index entry, detention, buffer busy ways. Doing it in a single bulk SQL statement, you can do in seconds or minutes what's going to take hours or days in the equivalent procedural code. There's a couple of pipeline functions, and that's to do with cardinality aspects. One is data. So, for example, here's a pipeline function, a very simple one that I use frequently. It allows me to query a string and turn it into a set, which means I can bind an in-list. And developers, they've got a list of things, the end user picks 5 things, and they want to say select star from the table where column in those 5 things. They can't figure out how to use bind variables with that, because if they pick 5, I need 5 bind variables. If they pick 10, I need 10 bind variables. So they end up doing the worst thing ever, string concatenation. And so they start submitting unique SQL to the database. And they start parsing like crazy, flooding the shared pool, all kinds of bad stuff. So I'm going to work around for this. So I have this little pipeline function that simply lets me put the delimited list in a string and query it as a table. Now there will be one line variable. But the problem with this is the database is going to give it an estimated cardinality of 8,168. If I wanted to change that cardinality, one of my choices would be to change my block size. I'm in an 8K block size database. If I went to a 4K block size, I'd have about 4,000. 16K, about 16,000. That's not the right approach, right? It's never going to be 8,168. It's going to be more like, well, there's about 10. They usually pick about 10 or 20. But if I run an in where it thinks there's 8,000 things coming out of it, it might stop using indexes to access the data. If it thinks there's 10 things in the list, yeah, it's going to use an index. 8,000 full scans hash counts. And so they say, you can't use bind variables in the wrong plan. So we need to fix this estimated cardinality. We have a couple of approaches. One is to use the cardinality here. This is undocumented, but it works with all releases. And the worst thing that can happen is that it stops working. Right? There's some undocumented stuff, but if you start using it, the worst thing that can happen is data corruption, wrong answers, bad things like that. The worst thing that can happen here is it just stops using it. But it works, and I think the estimated cardinality is correct. Another one is to use an op-estimate hint. And actually, in current releases, the cardinality hint is translated into an op-estimate hint. This one is also undocumented, but it's used by SQL profiles, introduced in version NG, and hence it's going to be around. Right? The cardinality hint isn't officially used in any piece of Oracle, but the op-estimate hint is. And it works with the scaling factor. So all I need to do is figure out, optimize by estimating 8,000 rows, I want to estimate 10, what do I need to multiply 8,000 by in order to get 10? And that's the scaling factor. So this is the second one. Here's the third one that doesn't involve changing the query. Use the extensible optimizer. Did you know that you can actually extend the optimizer and become part of the optimization process yourself? This is hidden away in a document called the Application Developer's Guide for Data Cartridges or something like this. It's a document that probably nobody here even think to read. I'm not going to go to cartridge, whatever that is. And this allows us to hook into the optimizer. So all of the code on the screen is boilerplate, will be the same for everything except for the stuff in red. And if you notice, the stuff in red are my two arguments to my function, my two inputs, the string and the delimiter. Then I implement a type body, and this type body is simply going to return the estimated cardinality. So I have a little piece of logic here that says, if I actually know what the string is, I'm going to count the commas in it. If I don't know what the string is, if it's null, I'm going to return the default of 10. And then I associate this package with that pipeline function. And the next time I run the query, here it does the default of 10. If I send a natural little string, it will really go through and figure out exactly how many were in there because we count those commas. Another one is to use dynamic sampling. This works in 11G and above. Here, if I use the dynamic sampling hint, the optimizer will actually sample the output of this function the first time we parse this query. And here it comes up with an estimated cardinality of 6. Which is pretty accurate because I had 1, 2, 3, A, B, C. It dynamically sampled the output of that function before it came up with the plan for optimizing the overall query. The last one is to rely on another new 11G feature, which is cardinality feedback. Cardinality feedback is the ability of the optimizer to learn from its mistakes. So here I run the query the first time, and I've got 8,000 as the estimated cardinality. The second time I run the query, the optimizer knows it made a mistake and it fixes itself. So this has the upside of correcting the problem. It has the downside of we got to run the query poorly at least once in order to get it to work better again in the future. So of these 5 approaches, the most sophisticated, the most transparent was the third, adding that extensible optimizer. Probably the easiest is to use the cardinality hint right in the query. You're not telling the optimizer what to do, you're giving the optimizer more information. So the cardinality hint is pretty safe, pretty easy to do, but if you can't change the query, go ahead and take a look at that extensible optimizer. This isn't really SQL, it's more of a database capability, but it really changed the way you can use SQL. I like to say that SQL Loader is the legacy data loading tool from the 20th century. If you're using it, stop using it. Start using external tables. Have you ever had a data file where you wanted to load a record if this column equaled this value, or that value, or the other value? Try doing that in SQL Loader. It's virtually impossible. You have to use multiple into classes. It's really ugly. If you want to do any sort of transformation, it's very hard to do in SQL Loader. If you wanted to take a SQL Loader and do it parallel to that path, it becomes very complex. You got to run multiple SQL loader processes, you have multiple log files to look through, multiple data files to look at. Doing parallel direct path load with an external table, it's trivial. It's one line of code. Insert append into my table, select star from the external table. That's my parallel direct path load. If I change the number of input files for the external table, I've changed my degree of parallelism. It's a very simple operation. And I can even take that external table and join it with other tables, layer on it, filter it, pivot it, do whatever I need to it. I can also do some really interesting things with external tables. Starting in 11.2 and actually in 10.205 and above. So anything that came out 10.205 or later, you can select star not just from a flat file, but from the output of a program. This opens up some interesting potential here. And recently when I was talking about a question, the person wanted to be able to assure themselves that for all of their auto-extend data files, there was at least room for 20% growth on the existing file system. Right? So if I had 5 files on a given output point, I needed to take their size, figure out what 20% growth meant for each file, add that up, and make sure there was at least that much free space on that volume in order for them to pass. If it wasn't, I'm running the red flag. In other words, I needed to join DBA data files with the operating system. Pretty hard to do, unless you know about this capability in external tables. So here I created a DF script. And so I'm doing DF with a set of inputs that gives me a pretty static sort of output, something that's easy to parse and format that the database can understand. But notice when I wrote this program, I didn't just call it DF, I called it bin DF. When you're writing scripts, I don't care if it's for external tables or DB with scheduler or anything, always use explicit paths. Never rely on the path. The reason you can't rely on the path is different for the database server than it is for you when you're running the command line. So when I'm running a script from my command line, it's using my environment. When the database runs it, it's using the database's environment. It's not going to be able to find DF maybe. Or even worse, it finds a different DF. Right? And so people can put Trojan horses and whatnot into the system. This using explicit paths, highly recommended. So now I can create an external table, create a table DF. It's got the same output, or the same format as the DF output. The type is Oracle Loader, it's got a default directory, but over on the far side it's got this new directive preprocessor. This is saying you're not going to read from the file at the bottom of the create table statement, but rather you're going to run this program, run df.sh, against this file. Think about what this means for some other loading things. Somebody gives you a gzip file, and they say, here's your input to load your database, and it's a couple hundred gigabytes. If you were to decompress it, it would be a couple thousand gigabytes perhaps, a really big file. So you don't want to decompress that file and then load it into the database. Well, you can write a shell script that unzips that to standard out, and you can load directly from the compressed file into the database without ever decompressing that file on the disk. But here, what I want to do is take the output DF and simply be able to select star from it. So I can select star from DF, from PS, from IOStat, from VMstat, from whatever you want. And I've sort of integrated all of these operating system utilities into the database. And I'm not going to go through exactly what this SQL query does. You can pick through it later at your own leisure. You have access to all these slides. But I'm using analytic functions and other advanced capabilities to sort of join DBA data files with the file system, find an outpoint with the longest name that matches my file name, keep that one, and then aggregate and make sure that I have that 20% extra capacity. So I need to know a couple of things here. I need to know about external tables, the preprocessor command, and how to use analytic functions. Because the join here is a little bit funky. The join between DBA data files and the file system data is where file name like something. It's not an equity join. So I had to sort of explore the results out so I could find the longest mount point, just keep that one with the row number as 1, and then do the computations on that. This is a pretty interesting approach. How can you want to hurt your head? If the previous three is like, this one's going to blow your mind. It was introduced into MG, and it gives you a spreadsheet inside of a SQL statement. But you can have a spreadsheet that's not limited to like 65,000 rows, but rather a spreadsheet that has as many columns as you want, as many rows as you want, billions in fact. It's adding procedural language to the SQL non-procedural language. So here's a question that I get frequently. I need to have running totals, okay? But I want to go through this sorted set of information, and as the running total hits some threshold, like 65,000, I would like that to be one group. So you can sort of iterate through this first set of data, adding up 10,000, 20,000, that gives me 30,000, and then adding 30,500, that gives me 60,500. If I was to add the next row 50,000, that would exceed that threshold. So I want to stop processing, output those three records as a group, reset all my counters, and do it over again. You can't do this in analytics. Because even though analytics can refer back a row and forward a row, they can't refer backwards a row and look at the output of an analytic function. The only thing you can do is look back a row and look at the previous count. Look back 2 rows and look at the previous count. You look back 20 rows at the previous counts. But you can't look at that running total and say, oh, if this would exceed 65,000, stop. That's what I want to partition by. So analytics don't work here. And I had gotten stuck in such a route, in such a way of handling stuff with analytics, where I thought, if I can't answer it with analytics, you can't answer it with SQL. I'm going to have to drop down the procedural code. So I thought maybe a pipeline function would work here, because what I need to do is keep that running total, when it gets to a certain threshold, change the group number, and then continue on to the next group, and it exceeds that threshold, go on and do that. So I was thinking very procedurally. So I came up with a pipeline function. And I said, what I need is a type that looks like my table, and I need to add a group number to it, because I'm going to do this grouping. And I'm going to write a pipeline function. The code's not extremely relevant. It's just going to take a cursor in, which is going to have the original input set, and it's keeping a running total. And every time the running total exceeds that threshold, I increment the group ID. So when it hits that 65,000 limit, I reset counters and I increment the group. So that if I run this pipeline function against this, I get that nice grouping that I want. The first 3 records all have the same group ID, the 4th record is in its own group, the next 2 are in group 3, and so on. And then all I have to do here is use some aggregation, and I've got the groups I want. I'm done, right? But I wrote a lot of code, more bugs, that sort of stuff. But I also wrote a lot of procedural code that's not going to perform very well. It's not going to perform nearly as well as a single SQL statement. So here it is, the model clause. This does exactly what my pipeline function did just a minute ago. It's a little bit confusing to read at first, but everything is until you get used to it. So let's walk through this sort of step by step. We've got the model clause, and with the model clause, we need some dimensions. Start thinking spreadsheets. Right? Spreadsheets have dimensions in them. I want to be able to subscript into my result set. Now here I need to deal with sort of the entire result set. So I added another column to my result set. I use row underscore number. And so I'm adding a row number to every single row inside of this result set. 1, 2, 3, 4, 5. So now I can reference procedurally row 1, row 2, and I could actually do a sort of a summation. You know, in a spreadsheet, you say sum of C1 dot dot C100, and then the next row might be the sum of C1 dot dot C101, right? And so you're doing all of these functions that reference sets of rows. So once I've added this dimension, it's going to sort of be my subscript. I needed to define what my measures, my outputs would be. And what I wanted in my output result set was a site. This would be my low site number. The second one is another site number. They look like they're the same enough because it's site S and site E. It should be the same because they're the same column coming out of the table. Well, down in the middle section, we'll get to in a minute, you can see that I've overridden the definition of what S is. So the first site is actually going to be a result of some computation, some spreadsheet function. So I've got the two site identifiers. I've got the original count, and then I've got the count again. But the count again is labeled SN, and SN is in the little section as well. By the way, a little backstory on this. This was asked on AskCon. I gave the parallel pipeline implementation, and somebody came along and said, why didn't you just do this? I said, well, of course, anybody can do that. It's simple. Mine is not so complex. Right? So I didn't write this model clause initially, but it really piqued my interest and said, made me think, I need to understand this, I need to learn this, because I set up a benchmark, and this was much faster as far as CPU utilization, passes on data, work being performed, than my pipeline implementation. So we have to define these measures. And I know I want a result set that looks something like the one on the bottom. And this is what I need to start working with. It gives me my grouping columns, the first column are my groups now. And I wanted the minimum site ID, the maximum site ID with some of those counts until they exceeded that threshold. So as we start walking through this result set, one by one, the first row is exactly the information from the database data. Why? Because as we look at our measures, they were site, count, and count, but one of the sites and one of the counts were overridden by a rule. But the rule is only enforced for row numbers greater than 1. So for Rn equal to 1, it just output what it got in. So that first row in the result set is exactly just the first row from the input screen after assigning a number to it. Row underscore number. Now let's move on to the second row. This is where it gets more interesting. Okay, the site and the count do come from the original table because the E column and the count column don't have a rule applied to it. So actually, if you look at my output result set, the E column and the count column always come from the original input set. But now, SN and S, row number is greater than 1, they're overriding themselves. So let's walk through those computations. This is basically saying, if I can look at the previous row's SN, CP is a built-in function. It's my substrate. It allows me to sort of look at the array of information. So if I take the current row minus 1, and I look back and I look at the SN column, which was a imputed column, and I add it to my count, so I take the 10,000 and I add it to the 30,000, or I add it to the 20,000 column, sorry, so I take 20,000, add it to 10,000. If that's greater than 65,000, or the current row's count is greater than 65,000, then I wanted to output the count of the current row, else I output the previous row's SN plus my count. So I'm taking the SN of 10,000, adding it to 20,000, that gives me 30,000. That doesn't match the first part of that case statement, so I output 30,000. And I do something similar for the second column. I'm looking at that in the first column, saying if I look back a row and I add this to that, if that exceeds 65,000, I want the next site, otherwise I want the current site. As I go to the next row, it gets more interesting. Those things get carried down, right? I now need to look at the SN column again. I'm going to look at the previous row's computation. This is what analytics can't do. I'm looking at the previous row's computation. Right? Not the previous row's value that it got from the result set, but the previous row's imputed value. Think of your spreadsheet now. When you write functions in your spreadsheet, you know that they're calculated in a very specific order. These are calculated in a very specific order as well. Like, imagine if your spreadsheet just picked a random cell and said, I'm going to start computing functions from here, and then I'm going to go up, and I'm going to go over, and I'm going to go down, and go around in circles to compute your functions. Right? It would never work. So we know functions in the spreadsheet are calculated in a order fashion. Same thing's happening here. So I can carry down the result of that computation to the third row. I can add the 30,000 to the 30,500. That does not exceed that 65,000. So I'm going to go ahead and output 65,500. the site ID and I do the same sort of computation, and I still get 1,001. Now I move on to the next row. This is where it becomes really interesting, because now I'm going to take the previous row, 60,500, add 50,000 to that. That exceeds my 65,000. So looking at the case statement, that first part is going to be true. And so when that is true, the thing exceeds 65,000, and I'm going to output the current row's count. And so notice 50,000 comes out. 50,000 is the current row's count. I reset my group, if you will. And when I go to the site column, this is going to output the current row's site, not the computed value of the previous row's site. So this has changed my group ID. Now you sort of see how this goes. It's going to take you a while to be able to write a query with the model clause. However, much like analytics, once you get the hang of it, once you learn a couple of the constructs, you'll be able to write some pretty impressive stuff. You know, we keep moving through here. The 50,000 plus the 25,000, that exceeds that threshold, create the next group, and so on. And so we get out of this model clause exactly the same set of information as we keep walking through it. As we got with my pipeline function, we get the groups. Once we can do that, we just need to add the aggregation to get the min and the max and the count value, and I get the same exact output. But I get it using a fraction of the CPU of the procedural approach. So it almost seems like I'm showing you things that obviate the prior stuff. I said analytics, coolest thing that happened in SQL. They can't answer this. Parallel the pipeline functions, really cool. You should look into using them, unless you're asking this question. Right? So each one of these things is good on their own, but you need to understand all of them so that you can apply any of them to a given problem instead of just sticking with one. I got stuck in a rut with analytics for a long, long time. Then this came along. This is extremely powerful. However, that said, 12C came out and gave us something else. And so here's another quick example. I've got some audit trail information, something with timestamps. And what I want to do is group everything by timestamps, but I want the groups to be such that every record in the group, after sorting by timestamp, is within 3 seconds of each other. So if you look through this information, the first 3 records are within 3 seconds of each other, but then that next record, the fourth one, is at time 12:22:45. The previous one was 12:22:04. That's more than 3 seconds. Build a new group. So, thinking about this procedurally, come up with some logic, and I sat down and said, analytics. I'm going to write some analytics. So I'm going to start by creating a table, put some of the data in, and here is the data simply. And I put a red box around the 3 different groups here. There's all the records in the first box within 3 seconds, but then the next record in 12:22:18, that's 6 seconds apart, so that's the next group. And the next 3 records are together, and then the next group begins. And so I need to find a SQL query that will give me those 3 groups, tell me the minimum time and the maximum time in each group, and sum up that Y column for me. So here's the analytics to do this. We're going to start by identifying where our groups start. And so what I'll do is I'll take X and Y, and I'll get the previous row's X, the previous row's timestamp. And so now I can take the current row's timestamp and the previous row's timestamp, and I can make sure that that's within 3 seconds. I can do this in that case statement. And when the difference between those 2 timestamps is greater than 3 seconds, I'm outputting a row number. Now, why am I doing this? So I can get a result set that looks like this. Notice after sorting by the timestamp, the first group all has null as their timestamp. The second group, the first record in it, has 11, but then is followed by nulls. The third group has 14, followed by nulls. What I need to do is carry down these values. So every record in a group has the same value. So I'm going to carry this down. It's another layer of analytics. So I take the first query, and then I apply a max analytic to it. Now I get this result set. The first group has all nulls, the next one has 11 once I've carried it down and I have these groupings, hopefully everybody will be able to finish the query by doing another level of inline reviews, doing min, max, and sum, grouping by, and we get the answer. I learned how to do this like in version 817, and I've applied it and reapplied it thousands of times since. In fact, I even call it the carry down method. It happens frequently that you want to do this. It happens over and over and over again. And so I really got stuck on a rut with this. But then 12c comes out, and there's this new row pattern matching clause, which allows me to apply irregular expressions to the data. Here is a technically superior way to write that same exact query. I'm going to take this set of data. So let's start from T. I'm using this new match recognize clause. In the match recognize clause, I need to take the data and sort it and order by X. Here, X is my primary key. The timestamp is unique, so I'm sorting deterministically. This is really important for these pattern matching clauses. Because if you're applying a pattern match to a set of information, and the order of the rows can change from execution to execution in the query, the answer can change from execution to execution in that query. So order by something deterministic. We'll come back to the measures in a minute. But we'll jump down to line 10. What was the requirement for this query? Take all the rows after sorting by timestamp, and for every set of rows, as you're going through it, if the current row is within 3 seconds of the previous row, it's still part of that group. So my pattern is find any row that is subsequently followed by another row within 3 seconds. Asterisk. It looks like the database has sort of figured out what we want to do. So I'm actually writing this out. But here's my pattern. And somebody said, just find a row. If it's followed by a row within 3 seconds, that's part of that group. If the next row is within 3 seconds of that, that's part of that group. And so on. So my pattern is simply find any starting row that's followed by any number of rows that are within 3 seconds. I have to define what another row within 3 seconds means. Right? And so get to the define section. Another row within 3 seconds is not part of the syntax of this row pattern matching. It's just a correlation name, an identifier I made up to make the query easier to read. Another row within 3 seconds is defined as my row minus the previous row is less than or equal to 3 seconds. Now the asterisk on the end of the pattern is part of the regular expression. That means I have to find any row that's followed by 0, 1, or more rows that satisfy this condition. So if you think about it, we go to the first row, that's any row. It matches that. So I've sorted this information by timestamp. The first row definitely matches the criteria for any row because there is no definition of it. Any row can match that. Now I go to the second row. I want to see if that's part of my pattern. So I take the second row's timestamp and then the first row's timestamp, subtract the two. If they're within 3 seconds, they match this pattern. And in fact, in this one, they would. You just remove the first 3 rows all grouped together. And so what this would do is on the first 3 rows, they're all part of this pattern. It is the fourth row. The fourth row is greater than 3 seconds away from the third row. Pattern's been matched. I found the first 3 records, they're all within 3 seconds. The fourth record is more than 3 seconds. So now I need to figure out what to do. I want to take those 3 rows and output them as a single row. And this way I did on line 8, 1 row per match. So I took my entire pattern and I said, I'm going to aggregate it. I just want 1 record out of this. The measures, lines 5, 6, and 7, tell me what I want to output. I'm using the first built-in function. Give me the first timestamp you saw in this pattern. Give me the last timestamp you saw in this pattern. And give me the sum of all the y's you found in this pattern. So this does exactly what that analytic function does. But it does it in one pass. After the match, line 9, skip past the last row. Where do I start looking for the next pattern? I could start on row 2, but that would be boring, because I find groups within groups within groups. I could start on the last row of the first pattern, but that wouldn't be exciting here. We already know it's not within 3 seconds of the next row. So I would position the cursor pointer to be the 4th row in this result set to start looking for the next group. And again, When you compare the performance of these two, this is a TK prof for the analytic function. Remember, I had an analytic function that I wrapped in parentheses, and another analytic function that I wrapped in parentheses that I did an aggregation on. This is all reflected in all those window sorts, window buffers, the hash group bytes, and so on. Here's the output of the TK prof for the not recognized. Use significantly less CPU, and everything in a single pass of the data. Oh, these TK profs are not for that tiny set of data. These TK profs are for something with almost 90,000 records in it, just to give you a sizable amount of information. I'm going to do one more row pattern matching. And this one, I sort of cheated because I just copied slides from last year. This is another example that drives this home. Stock information. I'm looking for a pattern in stocks. I want to find V-shapes. When the stocks try to high, when they go low, and when they went high again. So I want to find these V patterns. So I have a stock table. I created some stock information. And if I use SQL Plus, you can see this pattern easily. And I just use R pattern with asterisks, and I can sort of see the histogram, and I can see the V's. 13 rows, SQL Plus works great. 13 million rows, SQL Plus really works great. Right? You just scroll down too fast. Too much information. And really, from these 13 rows, what I want are 2 rows of output. I want to know what the high point is, the low point, and the next high point. Here's the query that can do this in a single pass for you. And so going through this again, let's start from stocks. We're going to order it by, we're going to partition it first. We're going to break it up by stock symbol. So I do Oracle, separate from Microsoft, separate from IBM. Within each stock symbol, I'm going to sort it by the timestamp. So now I've got my deterministic sorter within each of the stock symbols. Let's get down to the pattern. What do I want to find? I want to find a record that's followed by one or more downs, it's followed by one or more ups. So it's sort of like my previous pattern, but I'm using start as my any record, down plus. Instead of using asterisk, which means 0, 1 or more, I'm using plus, which means 1 or more. I need 1 or more down records, followed by 1 or more ups. What is a down record? Down is defined as my price on line 13 is less than my previous row's price. Up is conversely defined as my row's price is greater than the previous row's price. As I'm cursoring through this result set, the first record in the result set matches start, because it matches any record. I go to the second record and I verify it matches the down, so I've started matching my pattern. The third record is still a down record, still running my pattern. The fourth record is not a down record. I need to ensure that it matches the up criteria. Fourth record does, fifth record, sixth record, seventh record. Now the eighth record is not an up record. I've matched my pattern. I've matched the biggest pattern I can. So I go to my measures. What do I want as an output? I want my starting timestamp, the last down timestamp that I observed, that red row in the middle, and the last up timestamp. And I get that one row of output down at the bottom. Hopefully you can see this is a pretty powerful construct. Because you're thinking in regular expressions now. You're not thinking procedurally. Doing this in straight SQL without row pattern matching, finding this V-shaped pattern, really difficult. Can be done, but the SQL is hard. The previous example was sessionization, where I wanted every record within 3 seconds. You know you can do that in regular SQL because I showed you how to do it with layers of analytics over and over again. But you're scanning the data and scanning the data and scanning the data over and over again. That doesn't scale well around billions of rows. This, again, operated in a single pass from the data. This is significantly faster than trying to do it in vanilla SQL. This is almost like doing duplicate processing inside of the database. We can parallelize this, we can partition by clause, and everything can be done by separate parallel execution servers, and most importantly, it can be done in the single pass of the data. Amazingly, I've never given this set of slides before in my life, and it's exactly what I was learning, and I'm exactly done. So again, these slides will be up on the Oracle.com website. You'll be able to get them down and walk through the examples slowly yourself so you can figure it out. Thank you for your time.